Hi everyone, thanks for joining today. My name is Cameron Lowe. I'm a field applications engineer out of the Midwestern region for Tektronix. And today we're going to focus on power integrity measurements and signal integrity measurements using an oscilloscope-based solution. So we're going to start today by focusing on power integrity as a whole and sort of discussing what is power integrity, what do we mean by power integrity, and we'll jump into some of the key challenges throughout this presentation in preserving power integrity. So this is really going to focus on what are the things that you guys are seeing in your power supply development, and how do the downstream power rails that are being used by active components, whether it's serializers or FPGAs, how do the point of loads really rely on preserving power integrity to optimize their performance? And to do that, the demonstrations that I'm going to show today are really going to focus on using a very low noise solution from a scope perspective, but also it's going to feature our TPR power rail probe. And we'll talk a little bit more about what this probe is really ideal for, and how it can be used to help identify power integrity problems. So the three demonstrations that I'm going to highlight today are first going to focus on making high impedance probe coupling challenges. So the difference in making measurements using AC versus DC reject or DC coupling. And second, we're going to make measurements of very precise ripples. So we're going to be making ripple measurements on a power supply rail to some DDR memory. So a very sensitive voltage rail. And we're going to be making power supply ripple measurements, but not just on the ripple, but the actual ripple riding on top of ripple. So you'll see just how low a noise our power rail and scope solution can achieve. And then finally, we're going to focus on how do you maintain target impedance in a power supply or in a power distribution network. And to do that, we're going to be focusing on our frequency response analysis package that's included with our power measurement software tools. So that's what we're going to be focusing on for today's presentation, and then there will be a Q&A at the end of today where I can help answer any additional questions that may come up. So what do we mean by power integrity? Well, so if you're searching the web, you may find many different definitions of power integrity. There are three that we've captured here from various sources. But the summary of all of this is basically that the power supply or power network should be supplying the appropriate amount of power to the devices downstream, all at a noise level that is acceptable and does not disrupt any of the components that are being powered. So why do we care about power distribution networks and power integrity? Well, the image in the bottom right is a basic diagram of what a typical power distribution network looks like. It has DC to DC converters. It may have AC to DC converters further upstream. May have linear regulators down towards the point of load or PL sources. But the general sense is with Moore's law, and the concentration of electrical components into a smaller form factor, we're seeing embedded designs become more and more efficient, adding more functionalities, all with a reduced form factor or size and a reduced power consumption. And so what we're seeing is oftentimes signal integrity products or high-speed serial products or any of the systems included in our embedded systems environment are oftentimes becoming closer and closer to the power delivery path or the power integrity components. And so, as these devices become closer and closer together, they interfere with each other, they influence each other. And it's important overall to understand the impact that these two components have on each other. And so again, what we're going to be focusing on more within this particular webinar in the context is how power rails influence especially jitter and jitter sources, because we know that introducing noise and jitter from power rails can cause bit error rates in high-speed serial networks, which at the very least can reduce the efficiency of those embedded systems, but at the worst can lead to corrupted bits or corrupted data lines that fail in mission critical environments. And so all of this again is very important to understand from a PDN network. So there's obviously a wide variety of use cases for power applications, as they can power a number of different things. But from a testing perspective, we can broadly classify power applications into two segments. The first being kind of the high speed, low speed applications, where you're measuring especially DC voltages on the core rails of FPGAs or memory sensors or microprocessors, so on and so forth. And here the voltage levels can range, typically maxing out at about 3 volts, and the requirement from a testing perspective is usually measuring ripple or measuring what sort of AC injection is coming from a variety of different sources onto that DC rail. And because of this, the transitions that you see are typically higher speed, right up into the ISM band, a little bit greater than 2 gigahertz. And because the voltages are so small, we usually see a requirement for very precise resolution from a scope perspective, so tens of microvolts resolution, which broadly speaking means we need a high vertical accuracy from the scope, and we need a very low noise and oftentimes a very low attenuation type of probe to be able to make these kinds of measurements. And ultimately, these are the ones that are important for this webinar's discussion, because they focus on the ripple that again is coupled in from high-speed serial lines or has the ability to couple into high-speed serial lines and make an effect on the total jitter that's being assessed, or that can interrupt bits in the data stream. The other application is more of the high voltage applications, which you see in power supplies, the automotive segment, DC to DC converters, so on and so forth. And here the voltage levels can range usually from 5 to 48 volts, 28 volts being a fairly common mil-arrow type of DC bus. And the switching speeds here are oftentimes a little bit lower, and the real requirement from the testing perspective is usually a high DC offset, because for the most part, many of the probes that are out there to make these kinds of ripple measurements don't have the DC offset that's required, and so that's why you see things like the use of AC coupling. And we'll talk about the advantages and disadvantages of AC versus DC coupling here in a couple of slides. So let's now talk about some of the key problems that need to be solved in testing for power integrity and signal integrity. So the major problems can be assigned to 5 different areas, kind of highlighted in orange here. The first is the measurement system. So that includes the probing, the scope that's being used, the different measurement methods, whether they're automated or manual, any of the connectors that are being used out front of the probe tip. All of those are very important to understand what role they apply to the test. For example, additional probe leads can decrease the total bandwidth of the measurement system, not just the probe, but the scope itself. And so it's important to understand the bandwidth and common mode rejection roll-offs, just to name a few, with any of the connectors that you're assigning out front. The second is signal integrity versus power integrity. So this is crucial to understand within any of the systems that you're measuring power integrity on, because power integrity and signal integrity both influence each other. Noise from one can affect the other, and so it's very important to understand the root cause of where the noise is coming from. The third is the device response across a frequency range. So all devices vary over a frequency range, And in particular, it's important to understand the impedance and how the components under the power supply can vary over that impedance. What we'll see in a little bit later is a demonstration that shows basic passive components and how they vary over frequency. And all of that is used to decide what the base resonant frequency that needs to be selected for the power supply to keep everything in check. The fourth is the DC to DC power conversion stage. So this is a really critical stage, of course, for any power supply. Oftentimes here you've got the final stage or the point of load type of source, and so you're making sure that the components used here are filtering out any sort of ripple or transients or noise that's coming from the upstream power support sources. And then finally, the fifth is the AC to DC power conversion stage. So of course this is usually the first power step, and here again you need to maintain optimal power quality, ensuring that any sort of switching ripple that's included here is not being funneled downstream, all while maintaining a high efficiency. So in the diagram in this slide, we're highlighting the three major areas that affect the performance of a power distribution network, and that is power integrity, signal integrity, and EMI. So of course there's plenty of cases where you have individual issues within, say, signal integrity, and there's also overlap areas. And so in the worst case, all of these components lead to issues that exist across all of the three fields. And some examples that are included there are things like ground bounce or return path discontinuities, and all of those usually require the use of more decoupling caps used in the circuit. So some of the common problems that are linked to each area include things like attenuation, reflection, dispersion, crosstalk from a signal integrity perspective, voltage droop or switching noise or crosstalk included from a power integrity perspective. And in the EMI issues, we see things like near field coupling, radiated emissions, things that cause you to fail EMI compliance tests. All right, let's talk about some of the solutions that Tektronix has to offer for making these power rail measurements. So the probe that we're going to focus on and that I'm going to showcase throughout today's demonstrations is our power rail probe, and we offer two different bandwidth versions of this power rail probe: the TPR 1000, which is a 1 gigahertz probe, and the TPR 4000, which is 4 gigahertz bandwidth. Both of the probes in this family offer a number of features and specifications that allow it to make very precise ripple measurements on a DC power rail. And those include, first, the dynamic range, which is plus or minus 1 volt. That's usually sufficient for, again, making those very precise ripple and ripple on ripple measurements. And the offset range of plus or minus 60 volts is really critical here, especially when what we'll show in our next demonstration, which is it allows you to use the power rail probe in DC coupling with a fair amount of offset to measure all the way up to those, for example, 48 volt power rails that you might see in a data center. And the other key piece here is the system noise. So we've included all these features, and the system noise in conjunction with the very low attenuation that's used with this probe really allows you to see the true nature of the DC bus and all of the ripple that's included there. It's very hard to find a power rail probe out in the market that includes this level of noise, either at 20 megahertz bandwidth limit like it is often used, or at full full bandwidth, or I should say up to 4 gigahertz, which is the maximum bandwidth of this particular probe. The last piece I should highlight here is the connectivity options. We're going to cover that in a slide a little bit later on in the presentation, but we offer a wide variety of different connectivity options to give you the flexibility to move between the most convenient connection down to your device and the highest performance that's needed to really make those crucial measurements. All right, let's take a look at a example here of the difference between AC and DC coupling on a fairly low voltage power rail. So the demo board that I have in front of me is a Beagle Blackbone board, and I have a probe point on this board that is near the core rail of the SoC, or the system on chip, which in this case is a ARM processor from Texas Instruments. And then I have the solder point from that probe out to a MMCX connection point. That's the top image that you see there. I also have a push button on this board that activates a DVS sequence, or a dynamic voltage scaling sequence, on the SoC. So the use case is this. You've got the steady state voltage of your processor, which should be fairly low to make sure that it's drawing the minimal amount of power when not in use. But when the processor is tasked to do something more than the steady state voltage can require, the DVS capability of the SoC allows the core voltage to scale. So what we will expect to see on the scope is a DC offset as the core voltage kind of scales and tries to figure out what its optimum core voltage should be, and then ultimately it will drop back down to its steady state once it's completed its task. To capture the signal, we're going to use the TPR 4000, which is the power rail probe we discussed on the previous slide. And we're going to be comparing the AC coupling, or what we call DC reject, capabilities of the probe versus DC coupling. So we'll kind of see the nuances and why you may choose to use one versus the other. And the probe is plugged into my MSO64, which is our 25 gigasample per second, 8 gigahertz low noise oscilloscope that can get up to 16 bits of vertical resolution. So we'll see very fast rising edges thanks to the 25 gigasamples per second, and we'll see great vertical accuracy thanks to the 16 bits of vertical. Alright, so let's take a look at the scope now, and we'll view what this core rail looks like. So from a default setup, I'm using channel 4 on my oscilloscope here. We're going to take a look at what this power rail looks like. So I don't see anything on screen, but if I increase the vertical scale, we can see that our rail is riding right at 1 volt. So fairly low voltage core rail, like we would expect for something like this SoC here. And so you can see the coupling that's being used by default is DC coupling. But as I mentioned, what's commonly done to analyze especially the ripple on some of these rails is to do a DC reject or an AC coupling. So let's apply that, and we can see that the 1 volt offset that was included on that rail has now been effectively zeroed out. Okay, so now let's dial in some of our settings here to better view some of the ripple that we might expect on this rail. So to do that, I'm going to adjust first my vertical setting to something a little bit smaller, maybe like 50 millivolts per division. And I'm then going to go to my horizontal settings, and I'm going to scale out to something like maybe 400 millivolts, because I know that this particular signal is going to take a fairly long time to transition around to the different DC offsets. I'm also going to set the trigger position to 10% in this case to more adequately push the transitions onto the screen. I'm also going to set the acquisition mode to high res. What that will do is that's going to set the ADC to acquire 16 bits of vertical resolution. So you can see some of the noise is immediately averaged out using our high resolution mode. And then finally, I'm going to set our trigger settings to something a little bit more meaningful, maybe 40 millivolts up. And I'm also going to set our trigger to normal instead of auto, so that we're acquiring a waveform only when we meet that 40 millivolt threshold. And I'll set my acquisition to a single acquisition so that we're going to capture this pulse once things start transitioning around. So we saw what the steady state voltage looks like. Now let's see what happens when we activate this DVS sequence. So I'm going to press the push button on my BeagleBoard board. You'll see down in the bottom right hand corner that we've triggered. And okay, now we've got our waveform on screen. So the first things to notice here is we can see what appear to be different transition points in this sequence. There's some AC transition points or some different frequency jumps that occur off of our DC baseline, and we can see where those transition points occur slightly. It doesn't really tell us at what DC offset the core voltage has scaled to, of course, but we can sort of get a general sense of it. It's not really clear whether these large peaks indicate the greatest transition, or if these smaller peaks have anything to do with what's going on in this particular core rail. So the general synopsis is that with AC coupling for this particular rail, we're not really getting a good sense of what the complete picture is, and what the different offset jumps this particular core voltage is rising to. So now we're going to compare this result with using our traditional DC coupling and applying a DC offset to the channel instead, using our 60 volt offset range on the power rail probe. So I'll go back into our channel badge. I'll switch us back into DC coupling. I'm going to move us up to 1.1 volts in DC offset, and I'm going to move our position down slightly as well, so 1.2 4 divisions in this case, and we'll see why that's important here in a second. I'm also going to move our trigger up to match the offset level, so I'm going to move that to 1.1 volts as well. Alright, and so once again, I'll set my acquisition to acquire single, and I'll press the push button to activate the DVS sequence. You can see we've triggered on a pattern here, and we can quickly observe just the differences that adding in this information of the different DC offset values that are applied throughout the sequence can have. So we can see that what were the significant AC blips that we saw on the last screen are what appear to be indeed the DC transitions, as this pattern jumps from offset level to offset level. So you can see our pattern is basically we're scaling to a higher and higher voltage value, and then once we decide that there's no more work, or there's not a significant amount of work to be done here on the processor, we go back into sort of our sleep mode, back down at 1 volt. Now the DC transitions that we can see are a lot more complex than that. For example, if we zoom in on just this pattern here, what we'll notice is that the DC offset there is actually much more complex. So you can see there's transitions on transitions here. There's even different ripple and different noise values that are being coupled in each pattern. So there's a lot more complexity on this particular rail that was basically unnoticed once we coupled everything back down to zero, or to DC, or to ground in this case. All right, let's take a small step back now and cover why AC analysis is becoming so critical for power integrity. So as you can see in the block diagram here, this is kind of the typical AC to DC power conversion stage with switch mode power supplies and DC to DC converters. So this is something you would typically see in a voltage regulation module, or VRM. And the first source of switching ripple that's included here is usually from things like the transistors and MOSFETs, which are being switched during the operation of the power supply. So of course those generate a specific switching frequency, harmonics included there, so on and so forth. And so to keep the operation of the power supply smooth and to reduce noise downstream, oftentimes developers will use things like capacitors and inductors. But of course, all of these components and the different sizes and shapes of these components, whether they're surface mount or through hole, they all perform differently over different frequency ranges. And so it's crucial to understand the variety of different components being used in the switch mode power supply and how they are changing over specific frequencies. All right, for the second demo that we do here, we're going to now focus more on ripple measurements. So in this case, we're still using our Beagle Black bone board that we used in the previous demo. Now we've moved our test point to the bottom right MMCX connection. That particular test connection leads to a solder point near the DDR3 memory module rail, which is a 1.5 volt rail. So we're going to be measuring the ripple that's riding on top of that DC rail. And to do that, we're going to use two different probes and compare the results of which each of them capture the ripple effectively. So the first probe that we're going to use is our TPP1000. That's a 1 gigahertz 10x passive probe. It's the probe that we supply with all of our 5 and 6 series oscilloscopes. It's a very good probe, very low loading, and we're going to compare that against the TPR 4000, which is again our 4 gigahertz power rail probe. And I think what you'll see is the attenuation difference between a 10x passive probe and a 1x power rail probe is fairly significant, or I should say a 1.25x power rail probe. And we're still using our MSO64 low noise 16-bit vertical resolution oscilloscope. All right, starting from a default setup on channel 2, this is where I have plugged in my TPP1000. That again is the 1 gigahertz 10x passive probe that we're using here. So let's take a look at what the power rail looks like on this particular probe. So I know we need to set our offset to 1.5 volts, and when we do that, sure enough, we see a nice kind of steady rail right above 1.5 maybe. And so we'll dial in our vertical scale, maybe something down to 10 millivolts, and I can see we need to increase the offset just a little bit, maybe to 1.4, maybe 1.53 volts or so, just to kind of center that up right in the middle of the waveform here. And I'm also going to increase our horizontal span to something like 2 microseconds, just to capture a little bit longer of a record. So that gives us kind of the steady state of what this rail looks like. And you can see, sure enough, if I take a single acquisition here, there appears to be some ripple throughout, that like we would expect. It's fairly low voltage, certainly something that this DDR memory module can handle. But it's important to recognize what's going on here, and you can see that the noise that's included on this particular passive probe is sort of muddling out anything that's going on within the ripple that we see here. So you can see there's transitions at sort of the 10 microsecond mark here, and the 8 microsecond mark here, and the 4 microsecond mark here. But anything beyond that is really muddled between the noise of the probe. And that's purely because we're using a passive 10x probe. So all of the 10x attenuation that's included there is just multiplying the system level noise of the probe and the scope by 10x. And so for very sensitive rails like this, we're really unable to see any more information beyond that. Now, there are things we can do, like again using our high resolution mode to sort of muddle out that noise. If we apply that here, you can see it gets a little bit better, but still not significant enough for us to be able to see a divisive change in the noise level. The other resource we can use on the scope here is to apply a bandwidth filter, because oftentimes the high frequency ringing that you see here is just effectively noise captured from the outside environment. And it may not, it may mask over the signal like you can see here, or may not be useful for your particular measurement. So For the bandwidth filter on this particular channel, we'll limit it down to 20 megahertz and take another single acquisition. And you can see the ripple now becomes a little bit more apparent. There is some of these longer, let's say two microsecond duration ripple intervals. But again, we're not really seeing much more beyond that. Even if I zoom in on these single lines here, it's really hard to kind of see any sort of ripple on ripple measurement coming to light. All right, so now we're going to compare this against the TPR 4000 that's plugged in on channel 4 in this case. So starting from a default setup, once again, we'll configure the very similar settings to what we had, but now this time with our power rail probe. So I'll set my offset to 1.53 volts. I'll set my vertical scale to something like 10 millivolts. And I'll adjust our horizontal scale out to 2 microseconds per division. I'll set our trigger up to what we had before, so something like 1.53. And I will adjust the acquisition mode to high resolution, again to get those 12 bits vertical. And we'll go back and set a bandwidth limit of 20 megahertz. So you can see right off the bat a much cleaner signal, right? We're able to distinguish a little bit more of a ripple on this kind of declining line here. And what we can actually do is with the power rail probe, we can dial in a more sensitive vertical scale. So I can go down to something like 3 millivolts per division. And if I acquire again, now we can really see a pronounced ripple on ripple measurement, and I can actually zoom in on what this measurement looks like. So let's put cursors at these values, and to do that I'm going to apply the cursors, right click, move cursor A here, and right click again, move cursor B here, and you can see we're right at about, let's say 6 megahertz or so. So we're immediately able to correlate not just the slower or lower frequency ripple that we saw on this DC line, but some of the higher frequency ripple that we're seeing. All right, so next what we might want to do is let's correlate this ripple that we're seeing with the cursors here in the frequency domain. And so in the past, the way many engineers, including myself, have done that is use like a math FFT trace and try and work through the correlation there between analysis length in the time domain versus resolution bandwidth in the frequency domain. Sometimes that correlation can be tricky to overcome. Like you might see in this particular instance, we're capturing a 2 microsecond long, or 2 microsecond per division, 20 microseconds total acquisition length in the time domain, and really that correlates to a fairly coarse RBW in the frequency domain. And so to maintain both of those, we really want to use an analysis tool that allows us to have independent controls between the time and frequency domains. So for Tektronix and the scopes that we're using, including the 6 series that I'm showing you here, we have a feature called Spectrum View. So if I go into my channel 4 badge, go down to the Spectrum View display and turn it on, now you'll see my time domain view still remains at the bottom display, and the top display that's appeared now is a frequency representation of the same waveform that I've captured here. So what's nice about this is if you see the spectrum badge down here at the bottom, let me open that up, you'll see the center frequency that I've set here is 10 megahertz. The span that I've set here is 20 megahertz to couple in line with the 20 megahertz bandwidth filter that I'm using. And my RBW is set to a ratio between span and RBW. So currently you'll see it's set at 20 kilohertz, which is a fairly narrow RBW for this particular setting, and that again goes back to the independent controls that we develop within the actual ASIC of the oscilloscope. So we have true independent operation between the time and frequency domain controls here of the analysis. And so there's a couple of interesting things that I can now view in the frequency domain. So you'll see there's some fairly low frequency ripple, just like we're seeing with these kind of low frequency humps in the DC line. And then there's a peak where if I adjust my view and set my marker thresholds to be a little bit lower, now you'll see that there's a reference marker here that appears right at 6 megahertz, which is exactly in correlation with the cursors of the ripple on ripple that we were seeing when we zoomed in there. So, all right, so the last part of this is going to focus on making a ripple measurement. So I'm going to close out a spectrum view so that we have just the time domain window open. And we're going to add a ripple measurement, but first I want to just double check what the low frequency ripple that we see on the line is here. So again, I'll right click here and move cursor A to this hump, and right click over here and move cursor B to this section. So 230 kilohertz is the low frequency ripple that we see here. And again, that correlates back to that sort of low frequency hump that we saw in the frequency domain. So now I'll go into our measurement analysis menu. I'm going to access the DPM. This is for our digital power management software package. So you can see there's a number of different measurements included in this package, including ripple, like we're going to show here, some transient analysis to see, especially when you're turning on or turning off one of these power rails, what the overshoot and undershoot is. We have a power sequence analysis to be able to measure in conjunction with all the power rails that you're using what the total turn on and turn off time is, and then some jitter analysis to correlate what is the periodic nature or random nature of the jitter that you're seeing on some of these lines. So for the moment, we'll focus on our jitter analysis. I'm going to add 2 power rails to this measurement. That way we can pull in the lower frequency and ripple on ripple measurement. So I'll add this here. I'll go in and double click on this section and go into my configuration menu. And this is where we get to, basically assign the different values for each of the ripple measurements that we want to make. So what I'll do first is I'll set my first rail to be on channel 4 at the lower frequency, so 230 kilohertz with a 20 megahertz limit. And again, I'll set my second rail to be on channel 4 as well, but now at 6 megahertz to capture the ripple on ripple that we saw here. And again with a 20 megahertz limit. And now you can see these 2 measurements populated in the badge, the 1 being the lower frequency peaks here, and the 2 being the ripple on ripple that's being measured here, and it gives both RMS and peak-to-peak measurements. All right, now one of the key aspects in making these very precise ripple measurements has a lot to do with the connectivity options that you're going to use. At Tektronix, the power rail probe that we've developed, the TPR 1000 and 4000, uses a bare SMA female connection. So we offer many of the probe tips that we show from that SMA out to different leads. And again, the goal for us is to offer the most convenient, lowest inductance and lowest capacitance tip that's available out to the full bandwidth of what's required. So as I said, we offer a number of different options. They include SMA to MMCX. MMCX is traditionally been more of an RF based application kind of connector, but it is a shielded barrel connection for differential measurements. And what's nice about that is for power rail measurements, it allows the user to click in to the SMA barrel with our MMCX tip, and then the barrel of the connector itself actually shields from outside noise that might couple into your measurement. So from a performance standpoint, MMCX has served very well for both power rail probes as well as some of the other high performance probes that we have in our portfolio. For the power rail, we offer two different cables. We have an SMA to MMCX that you see here, and then we also have a high temperature cable. For those of you using and evaluating power rails in a temperature chamber as an example. In some cases, we understand that the board layout and design is already spun, and so additional test points like MMCX barrels cannot be added. So we've included different semi-permanent connections within our power rail portfolio as well. We have solder-in adapters that connect to different test points, and of course, the challenge with these is, getting a good solder connection can be sometimes more of an art form. But for those that can, the solder on tips are a good option for getting as close as possible. We offer some solder wire to get down to the nearest capacitor or whatever test point you're trying to solder down to. And just as long as the tips from that solder are not substantially long, we won't be inducing a significant amount of inductance into the measurement. And then for the best convenience type of measurement, we do have a browser tip, which is very similar to some of the pointed tips that are offered with many of our passive probes. So it has the witch's hat, kind of the pogo pin that sticks out, and allows the user to move around to different points on board just for kind of a quick and dirty measurement. All right, we're going to move into our final topic here, which has to do with impedance and how it can vary through the operational frequency of a power supply. So the key consideration for PDN or power distribution networks is the target impedance, which represents the upper limit that should be maintained within the system so that the power supply noise doesn't exceed its maximum value. And every PDN has a target impedance that's set around the operational frequency in the ideal state that's usually included within the design stage, and all components have to operate with minimum impedance at those frequency ranges. If the target impedance increases the target, then usually designers will include different types of capacitors to lower that target impedance. And the capacitors will lower the target impedance with the goal of not affecting the overall PDN's performance. Now, capacitors, both in parallel and series, obviously introduce a variety of different frequency changes, and they also raise the cost of the power supply in general. So the goal here is to develop the target impedance so that the least number of decoupling caps, as an example, are used, and the overall target impedance is achieved. So let's dive a little bit deeper into especially decoupling caps used within PDN networks. So decoupling caps, have two different goals. One, at its base, is to charge the supply, and the second is used for filtering. Again, shunting out noise that's being coupled from an upstream part of the power supply down to ground. And the overall goal of the decoupling caps is to reduce the overall impedance of the PDN. But keep in mind that obviously capacitors exhibit their own impedance profile over a frequency range, and the frequency at which the impedance is lowest is what we call resonance frequency. So that's the desired range where we'd like to operate the power supply given the capacitors used within the PDN. At high frequencies, capacitors actually behave like inductors, and this leads to what we call parasitic inductance. So now let's understand the different measurements that are used to analyze the impedance or the response of a power supply over a frequency range. So the three most common measurements that are used are control loop response, power supply rejection ratio, and overall impedance. So there's several different ways to measure control loop response. Tektronix, we use our Bodhi plot approach on the oscilloscope. So for this, we're using the scope as the frequency response analyzer. In this case, we use two channels where the first channel is analyzing the V in, or the input to the power supply, and V out is being measured by a second channel. There's an injection transformer that's used to inject the signal, usually from the function generator on the back of our oscilloscope, into the power supply without impacting the performance of the loop. And it's important that we don't inject any DC voltage, right? In this case, we're injecting basically a sine wave that we're sweeping over a given frequency range. And again, the overall goal here is to measure the phase and gain margin and determine at which points the power supply in question is working in a stable environment. The second measurement is power supply rejection ratio. So again, this is a similar type of measurement where, again, we're injecting a known sine wave from usually the function generator on the back of the scope. And we're measuring both the input to the power supply and the output on a second channel. And because we know what the generated power supply we know what the generated sine wave should look like. We know what the expected rejection result should look like. And so we're measuring how well the power supply does in rejecting the input sinusoidal wave. And then finally is impedance. So impedance usually is done with a vector network analyzer, or it's most commonly developed through network analyzers. However, there's a couple of measurements that really preclude using a VNA for PDN type of impedance responses. One part is VNAs are usually very good at measuring high frequency response, say across different cables or PCB traces. However, they usually don't do very well at measuring low frequencies or measuring very low impedance values. So the oscilloscope-based method that we use within our power measurement analysis software can measure down to as low as 1 hertz, so right around the DC value that you would expect an oscilloscope to measure to. And thanks to the use of components like spectrum view built into our oscilloscope, we can measure very, very low noise type of systems, and that allows us to achieve very, very small impedance measurements down below 1 milliohm type of values. So this is a setup for our final demonstration today. So this is again making an impedance measurement across any type of device, but in this case a voltage regulation monitor. So the setup that we have here again is using a 4, 5, or 6 series oscilloscope from Tektronix. It's using the built-in function generator from our scope. We do have the option to use an external function generator like our AFG 31000. That's used mainly if higher bandwidth is required. We're also using a variety of external components from a company called Picotest. Those include a very high power supply rejection ratio power supply, which we're using to power the VRM itself, a active splitter, which again is splitting the input voltage coming from the AFG and going into both the channel 1 from an input perspective and into the device under test. And then finally, a common mode transformer to help break the ground loop between the device under test and the scope. And then finally, from a connection standpoint back on the scope side, we can use a couple of different options. The first would be using the bare BNC connections back to the scope channels, or through an SMA connection with an appropriate adapter there. And that can be done using the same 50 ohm or high Z kind of termination schemes that any scope can offer. In this case, especially on the 50 ohm termination side, we generally recommend a DC block to protect the front end of the scope from high voltage type of situations. The other option that you have, though, is using one of our power rail probes that we offer. Those have a bare SMA connection and can utilize some of the features included with the TechVPI or Tech Versatile Probe interface. So what I'm showing here is the output from an impedance measurement using a MSO6 series oscilloscope. The device under test in this particular case was just a very low impedance, low resistance resistor in this case. And so what we see in the plot, which is showing impedance in the y-axis versus frequency in the x-axis, is that just as we would expect from a resistor, the impedance value is sort of flatlined at 100 hertz out to about 100 kilohertz. And then at that point, you start to see the device become a little bit more of a reacted type of device. And so we're seeing the impedance actually increase from there on out. So the measurement that you see in the upper right corner is showing 3 different peaks that can be specified across the range here. And this is really just to show the low impedance values that can be measured using a very low noise oscilloscope like the 6 series. So this is just one example of again, a passive component that can be measured, but the same concept can hold true with the power supply in general. And there you'd see a much more varying kind of impedance response as you're going through all the different decoupling caps that we discussed earlier. So this concludes, the presented material that we had for today. Again, I hope you can see the value in using an oscilloscope-based solution to make these very critical power measurements. And I hope that you can also take away just the importance of looking at the response of a power design network and its effect on external circuitry from a signal integrity perspective, and also the influence from external networks onto the power supply rails that you're developing. So again, I want to thank you guys very much for your time today. I appreciate everyone attending. I believe there's going to be a Q&A session now where I can answer any additional questions that you have.